From a descriptive statistics perspective, I was very happy with the exam. If you have specific questions, please feel free to come talk to me. There will be a follow-up reflection on the exam coming as a separate assignment on Canvas in the next 24 hours. You should have it by tomorrow. Simply forgot to move it into this course, but it'll be similar to the last question on the exam. I'll ask you to reflect upon what went well and what didn't in the exam and what you can do to see how to improve in the future. We'll talk about that a little more. The following table appears on page 170 in the text. This is an example of a contingency table. There are 360 students in a given MBA program. They're broken into three categories: full-time students, part-time students, and those in the executive MBA, which is a different version of the program. We measure student engagement, frequency that we find them in Canvas, frequency that we find them in office hours, all sorts of different ways we measure engagement. Broad categories: low, medium, and high. Engagement 1, 2, and 3. This is basically the two-dimensional version of a frequency distribution. I've got two different categories here. I could extend this further and do 3 or 4 or 5. Any sort of database can be arranged in this sort of fashion to be a contingency table. We rarely see them using more than 3 variables at this level. And I'm really only going to focus on 2. But I have all this information. Down at the bottom, the very last row, I have the column totals. All the way on the right, I have the row totals. All the way here in this bottom right corner, total number of students. So I can ask for probabilities because you have the entire sample space and you have everything broken down within that sample space. From here, I could ask, I pick a student at random from the MBA program. What is the chance they are of medium engagement? How many students are in the medium engagement column? Yes. Exactly. I take the number here and divide it by the total. The probability that a student is part-time. Tony? Out of the 360, yes, 88 out of 360. These are referred to as marginal probabilities. Because they're working with the totals on the margins. It's a row or a column total against the overarching total. I've used the following phrase before. What is a joint probability? So it's an and. Well, if it's an and, what set idea went with an and? Picture my Venn diagram. Which one went with and? The intersection. Well, if I'm taking intersections, then a joint probability is going to represent the probability of an and. It's going to represent an intersection of a column and a row. There's no overlap between students within the categories that make up the rows. There's no overlap between the students that make up the columns, but a joint probability is an and. So we intersect a row and a column. So I could ask, what is the probability of being of medium engagement and being part-time? Again, this is out of the total. There are 360 total students. How many fit this category? This table is on page 170, so I don't have to keep sliding back and forth. You can pull it up on your book. But let's go back up there. E2 and M2. Out of, right, because I need this to be a probability. It's got to be a number between 0 and 1. There we go. I can turn all of these into percentages if you want. That's completely your choice. I could actually do that within the table itself. Back up here by dividing everything by 360, just putting a 1 in this corner. That would turn our frequency distribution into a relative frequency distribution. There might be a little bit of round off error though, depending on how many decimal places I go out. I don't know, what's 7 divided by 360? That's one of those repeating decimals. It's not going to be pretty. If I have individual events and I have ands, I can do conditional probability. So let's think about, again, using our same example of being a part-time student and of medium engagement. Let's look at this idea. What is the probability that a student is of medium engagement given that I have chosen a part-time student? What does the given do to my sample space? By reducing it to what? Not numerically, but in terms of the ideas up there. It reduces me to only being allowed to look at that row. The condition, I've already chosen a medium, a part-time student, M2. Given M2, I've reduced my sample space to being that row only. Oh, wait a second. I'm no longer looking at all 360 students. The denominator of this fraction is 88. So now I've restricted myself to only looking at that. Well, in that case, if I'm looking at E2 given M2, it's what out of 88? Exactly. Please notice, if we were to use the formula for conditional probability, the formula says P of A given B is P of A and B over P of B. I just scrolled it off the top of the page. What is the probability of being in M2? A probability has to be a fraction. What's the probability of M2? Exactly. And we already calculated the probability of E2 and M2. That's right here. And notice I've got over 360 on the top and over 360 on the bottom. They would cancel, leaving me exactly the 17 out of 88 we got from the table directly. By the way, this allows me to check independence fairly directly. Are E2 and M2 independent? What was our definition for independence? It's independent if the probability of if what doesn't affect what. Right, the outcome of one doesn't affect the outcome of the other. So if I were to say we're looking at E2 given M2, I'd want to compare that to what other probability? E2 and M2 are independent if probability of E2 given M2 is the same as the probability of what? Unfortunately, no. The resulting other piece is no longer conditional. Unfortunately, no. The probability of being zero would mean it would never happen. I want to know if knowing M2 affects my knowledge about E2. If it doesn't, then the chance of knowing about E2 should remain the same, whether or not I know about M2. So the probability of A given B is going to be equal to the probability of A. That's what it means to be independent. The extra knowledge didn't gain me any information one way or the other. Well, now I can just look at the numbers. We know P of E2. Scroll back up the page. P of E2 is 53 over 360. Somebody give me a decimal. What's 53 over 360? $147. P of E2 given M2 was right here, 17 over 88. What's 17 over 88 as a decimal? Those are not equal. Therefore, these are not independent. I'm very loath to use the word dependent as opposed to saying not independent. Dependent to me makes it seem like there's some sort of cause and effect involved here. I don't know that being a part-time student causes you to have a different kind of engagement than being a full-time student, than being an executive MBA student. I simply know that it is different. I don't have cause. So as much as I can say the opposite of independent is dependent, I hate using that word. What if I did it the other way? What if I did M2 given E2? What does this represent? Not what's the number. What does this probability mean in words? Emily?
Does the Does the probability of one thing in the population of the whole thing, the whole chart, the same as the population of just a small group? Or not the population, the same probability of a small group? So, like with cards, if you
I literally don't want to talk about anything other than this scenario. In terms of the MBA students, and M being which part of the MBA program they're in, and E being the engagement. Well, up here, we said, this is the chance, E2 given M2. This is the chance a student has medium engagement if we know they're a part-time student. What's this one mean?
the probability of them being a part-time student, given that they have medium engagement.
Aha. So I've reversed the role of what I know in advance. I know the student has medium engagement. How does this change what I do on the table? So now I'm working with the medium engagement column instead of working with the part-time row. Everything else is set up exactly the same. So the chance that a student is part-time, given that they have medium engagement, is going to be out of 53 instead of out of 88, because I'm looking at that middle column. The numerator is still 17, but that's fine. That's the and. And again, if I were to compare this to something to ask if these were independent, what would I compare this to? Probably M2, the first one. But again, we have that number from earlier. The probability of M2 was 88 over 360, which is pretty close to 0.25. Is that pretty close to 0.25? Oh, very different, right? 0.32 versus something close to 0.25. So again, these are not independent. The whole benefit to using a contingency table is that individual cells as joint probabilities give me much more access to more things. Here's the exact same table on page 172, converted into 4 decimal place decimals. That's relative frequency. In the bottom right corner, I get 1, 360 out of 360. But I now have row totals and column totals as percentages, decimals, but still. And this works the same way. Problem 41. If you buy a glass bottled beverage here in the state of Pennsylvania, I don't remember whether or not there's a deposit law in this town. A bunch of them, bunch of states, offer you a nickel back for every glass bottle you bring back. It's actually printed on the label. So, if a state has a deposit law, people can recycle or not. If it doesn't have a deposit law, people can recycle or not. We surveyed 1,000 people. Here's what we got. Let's go through those 4 questions. What is the probability that somebody recycles bottles? Felix? Recycles, 340 out of 1,000, 34%. What is the chance they don't recycle given that they live in a state with a deposit law? The probability of the consumer who lives in a state with a deposit law does not recycle. So the given is they live in a state with a deposit law. Because I'm going to reduce myself to this first column here. I live in a state with a deposit law. I only care about this first column. And then I want to know they don't recycle. 66 out of 220. 66 out of 220 is 30%. 66 over 22. Percentage of consumers who recycle and live in a state with a deposit law. And this is a joint, not a conditional. So I just need one cell against the whole population. 154 over 1,000. It wanted as a percentage. I moved the decimal place 15.4%. Percentage of consumers in states with deposit laws who do recycle. There are two different ways to answer this question. Ellie? What are you punching up? Talk to me. How did you get the number? Okay, so that means I look at this first row, right? That means the given is that they recycle. But let's read the question again. Percentage of consumers in states with deposit law who recycle. So I want to know the given being they live in a state with a deposit law. Do they recycle or not? I think I'm back to the column rather than the row. See how you reversed the two? This is a common maneuver. It's why it pays to read slowly, and it's a pain in the ass because what we said first was not the thing I wanted to compute first. English hard, math easy, English hard. It's annoying. All right, what's the other way to do this rather than say, oh, I want 154 out of 220? The other way, let's go back to the question we already answered. We figured out the probability the consumer who lives in a state with deposit law doesn't recycle. Now we're asking, they live in a state with deposit law, they do recycle. Aren't those complements to each other? The answer to the first one was 30%. That means the answer to the second one is 70%. What's 154 divided by 220? Hot damn, 0.7. Contingency tables make my life easier because the numbers are all sitting there for me. Problem is knowing which number to use when. If you've done the Excel course and have learned about pivot tables are contingency tables. So I can take my giant pile of data, pump out a pivot table, categorize all the things I want in different ways, then pull probabilities till the cows come home. Questions? I am a very visual person. Frequently, I will start with something like a contingency table and then build another visualization. A tree diagram or decision tree. Let's start with a contingency table. I have a set of funds. Some are bond funds, some are stock funds. They have different expense ratios based on the firm that does the oversight. And now I can ask all sorts of questions about what my contingencies are. How do I say this properly? Which part of my contingency do I want to be the given in my conditional? So, do you want to break these up first by type of fund and then look at expense ratio? Or do you want to look at expense ratio first and then type of fund? We can do it both ways. Shall we do type of fund first or expense ratio first? Expense ratio. If I'm going to do expense ratio first, I'm going to think about the branches in a tree. Expense ratio can either be low or medium or high. And each of these numbers, each of these branches, is going to get a probability. The probability are the marginal probabilities for each direction. What is the marginal probability that I pick a random fund and it's in the low expense category? Because I'm using the margin here. So this one gets 14 out of 44, 16 out of 44, and 14 out of 44 again. Now each of these has a subsequent set of branches. And those branches are bond and stock. And each of these branches gets a probability. But these are conditional probabilities. Because we've already moved down one branch, right? We've moved down the low branch. Now I have to decide if I'm in low, what's the chance I'm a bond? What's the chance I'm a stock? So if I'm in low, chance of being a bond fund is 11 out of 14. The chance of being a stock fund is 3 out of 14. Repeat 2 more times. The chance of being a bond fund, if you're in the medium category, is 7 out of 16. The chance of being a stock fund in the medium category, given that you're already in the medium category, is 9 out of 16. And similarly, down here, bond 3 out of 14, stock 11 out of 14. Please notice, in a number of places, I have some really nice totals. If you add up those 3 numbers, what do you get? $14 and 16 and 14 is 44 over 44. I get a 1. Here, here, and here. All branches that come off the same point, going left to right, sum up to 1. Every time. Why? Because the rows have to total the number on the end of the row. The columns have to total the number on the bottom of the column. Within the rows, within the column. By the way, I did it the other way around. I went bond and stock first and then branched low, medium, high off each of those. Same thing is true. Add those numbers together, you get 1. Add those 3 together, you get 1. Add those 3 together, you get 1. It is quite possible to make a decision tree with more than 2 layers. Again, we talked about a contingency possibility, contingency table for more variables. It's hard to visualize though, isn't it? I'd have a 3-dimensional table. No, this is where we get into databases. But I could put more branches on here, couldn't I? I could just nest these branches going out further. This is actually a better visual for more complicated problems than a table is. Questions? I said these probabilities were marginal probabilities. I also said that the probabilities here in this second set of branches were conditional probabilities. They are the probability of being bond or stock given that you are in the low, medium, high category. So it's the probability of A1 given A2. Maybe I should have written those numbers the other way, A2, A1, because it's the second layer and the first layer, whichever way you want to write them. There's a type of probability that's missing here. I have marginal, I have conditional, I don't have well, aren't marginals unconditional? They're just asking about one thing. Joint. I don't have any ands. How do I get joint probabilities out of here?
Go through both lines of the.
I want A and B, right? Means I start all the way from the root over there on the left, work my way all the way to the end of a branch, multiplying as I go. So the chance of being in the medium expense ratio and bond means I start here and go here, and I multiply those two numbers together. So the probability of being medium ratio and bond is the probability of medium times the probability of bond given medium. And the probability of bond given medium is exactly the probability in the second layer of numbers, the conditionals we got. And so in this case, that's 16 over 44 times 7 over 16. Hey, the 16s cancel. 7 over 44. Now, I don't know, Tony, if this is what you meant by unconditional, because that's really the probability of one box against the whole total. But that's where our joint probabilities come from, is multiplying down the line, because that's what our conditional probability formula tells us works. Yes, ma'am.
And cost of probability, what would you call that?
And because I have 6 total ending spots on my tree, I can have 6 total joint probabilities. In this case, that makes sense. There were 3 options in one and 2 options in the other. That gives me 6 total options. I got to talk about those rules too. Questions? Because I already have this decision tree that came from a contingency table, I said we could break it up either way and do the expense ratio followed by bond or stock fund type, or do fund type followed by expense ratio. As a matter of fact, in the textbook, they did bond type stock first, fund type, and then expense ratio, page 177. Here's the same the same information from the same contingency table, worked the decision tree backwards. But sometimes what I'm actually given is the information from a tree without the table. And I may not be given the information I wanted. I may want the information the other way around. I've only been provided this information. This is a really weird idea. If I have conditional probability but my condition is backwards, how do I fix that? So I'm going to give you what I consider to be a reasonably relevant example. I got drug tested. The drug test has a 5% chance of showing a false positive. What does it mean to have a false positive result?
It'll show that you're doing drugs, but you're not.
The test is positive, but I'm clean. There's also a 10% chance of a false negative. Now, some people will ask, are these realistic? No idea. I made numbers up for convenience. Here's the deal. I know I'm clean. The people who are doing the test have no idea. All they know, here's your test results. This is the question that really needs to be asked. I tested positive. What's the chance they caught me actually using drugs? Okay, wait a second. Wait a second. I need to make an assumption about the population of people who are getting tested. And I'm going to steal numbers from the Office of National Drug Control Policy, and they say that drug use in people my age is about 4%. Now, there is a rule developed by a mathematician by the name of Bayes. And Bayes figured out how mathematically to write out the formula for reversing the conditions on my probability. I'm going to give you this formula, and then I'm going to tell you I don't want to use the formula. I want to use the tree. You see how we're going from P of A given B and P of B to P of B given A? We're reversing the roles of A and B. This is written out with just two options in each case, A and B only being two things. There is a version that does a lot more. P of B given A is P of A given B times P of B over, now this is where it starts to get ugly, P of A given B times P of B, that's exactly what we just had, plus P of A given not B, P of not B. Remember that prime means the complement. Bleh. Now, this rule is, in my opinion, completely non-intuitive. I hate the way this rule looks when I look at the formula here. It doesn't make very much sense to me. But I think we can use the information we have to build a tree and then build the table. And then I can reverse the table, can't I? Because if I have the table, I can just read the rows instead of the columns, or the columns instead of the rows, whichever way I want to write it. So I'm going to take this formula and cover it up. I want you to have the formula, but I'm going to cover it for the moment. Let's go back up here. My question is, if I test positive, what's the chance I use drugs? But what does the information up here and here tell me? I need a notation. Let's let P of D be the chance a person uses drugs. And then I can think of positive or negative as my test result, right? So this last sentence right here, this sentence means what for this? This sentence right here means that this probability is 0.04. 4% chance, right? So what's the chance somebody doesn't use drugs? That's our complement. 0.96. Now I can use these things up here. So let's slide back up so I have that information above available to me. A false positive. What does it mean for a test to be false positive? We said this earlier. And the test showed positive. So the 5% chance of a false positive is the chance of a positive test given the person does not use drugs. They don't use drugs, but it still showed up positive. That's 0.05. Wait a minute. If that's the chance positive not using drugs, negative not using drugs is 0.95. That's my complement. Okay, that dealt with the false positives. Let's look at the false negatives. What does it mean for a test to be false negative? Aha, the person uses drugs but tested negative. So a negative test given they use drugs is 10%, which means a positive test given that they use drugs is 0.9. I can split the world now looking at the way these are made up into a set of branches. The first layer of branches is, do they use drugs or not? The next layer of branches is, was the test positive or negative? Because these are marginal probabilities and these are conditional. So if I get to here, I start at this one. Chance of drug use is 0.04. Chance of no drug use is 0.96. What are here and here?
Point 0.90 and 0.10.
Because those have to add up to 1. And those are given the condition that we already started by saying this person uses drugs. That means down here, it's point positive with drugs, with no drugs, 0.05 and 0.95. What numbers can I fill in here? Here, if I fill in a single box, that's a joint probability. We haven't worked out a joint probability yet, have we? So I have some work to do to get there. What numbers can I fill in here? Which totals?
The positive and negative totals as well as the drug use totals to be able to add up on. I'm doing it.
I can only insert these two totals because these are the only ones I know at the moment. I don't know these two totals. But I do know that if I multiply here and here, what do I get for this number? What's 0.9 times 0.04? What's point 1 times 0.04. Those are my joint probabilities, Tony. So this is D plus the 0.036 goes here. And the 0.004 goes here. And notice those add up to 0.04, right? Let's multiply this way. 0.96 times 0.05. And 0.96 times 0.95. Now I can add down. This is 0.916, and this is 0.084. Now I want to know what's the chance you use drugs if you had a positive test. If you had a positive test means you're restricted to that column. What's the chance you use drugs if you're in that column?
6 out of 0.084.
Which is, what's 36 divided by 84? %43. If you test positive, it's not a 5% chance. It's a much higher chance. People, this is what happens in real medical testing, which is why they make you do more than one test. You throw a positive flag on a drug test, they're going to make you take it again. Chance you do it twice in a row, then something's probably going on. We should talk about that. That is where we will pick up on Wednesday. Hope you all have a wonderful rest of your day. By the way, if you use the formula, you get the same result.